different types of communication, etc. Okay, so we have basically the type of communication we can classify based on the nature of the information and based on the signal communication, that is, it is whether it is unidirectional or bidirectional, and also based on the techniques of transmission. So here we have three categories, basic categories, and out of which again it is further classified the type of communication based on the direction of communication. It is simplex or half duplex or full duplex. So let us see each mode of communication classification. So if it is going to be the nature of the information, it is analog or digital, and techniques of transmission, whether it is baseband communication or communication using modulation. So all these are different categories how we are going to classify the type of communication. Okay, so we'll see one by one the different categories. So first, the electronic communications are classified according to whether they are unidirectional or bidirectional. So if it is unidirectional, we call it as one way, or it is simplex communication. So you would have heard of one-way communication. So in the previous days, we used radio communication, which is also kind of one-way communication, and TV broadcasting is also one-way communication. So where the user is sitting at one place and the data has been telecasted, and also we have used beepers or pagers, so where we can only receive the text. So all these are one way communication, so which is also kind of transmission, which is a simplex transmission. And the second mode is called the full duplex communication. So here people can talk and listen simultaneously. So here the type of communication, it is telephonic communication. So this is called as full duplex. So in the channel can be utilized all the time, and we can transmit as well as receive the data. And half duplex communication, so we can it is a two-way form of communication in which only one party transmit at a time, which is called as half duplex. So the channel can be used, but only one party can transmit. So these are some of the examples, like police, military communications. So they are using the radio frequency band of communication. So so you can, this is the kind of instrument which is used for the military or the police radio transmissions. And the frequency band you can use from 3 hertz to 300 gigahertz. So this is the frequency band. Depends on the application. The band of frequencies can be used for the military applications, police or the military applications. So all these are half duplex communication. So then citizens band radio. So this is again which is one of the short distance radio communication, whose frequency band extends from 26.957 megahertz to 27.283 megahertz. So again, this is a kind of radio communication which is band limited, and it is around 27 megahertz, nearly 27 megahertz. So this is a kind of one way, that is a two-way half duplex communication. And family radio is again one of the personal radio services, uses channelized frequencies around 462 and 467 megahertz. So it's something in the ultra high frequency band. And in order to avoid interference from the citizens band, so this again this family radio, personal radio services are used in the ultra high frequency band communications. And this is amateur radio, which is again one of the non-commercial exchange of messages, and it is used for emergency communication. So all these are different examples of half duplex communication. And how do we classify based on the nature of the information? So this is the first classification based on the direction of communication, that is whether it is half duplex or full duplex. So this classification is based on the nature of the information signal, so based on the data, so whether it is analog or digital. So if it is analog systems, again we classify this as continuous wave system and pulse modulation system. So if you want, you please take down this basic category. You can please just note down this basic category.
Noted.
Okay. So now we have based on the nature of the information signal. So again, this is classified as analog and digital data. So in analog, we have continuous wave modulation as well as the pulse modulation. So in continuous wave modulation, the difference here being that in continuous wave, both the carrier signal and the baseband or the message signal are going to be continuous. So they are going to be a sine wave. So that is continuous wave system. In pulse modulation, we are going to use the carrier signal as a pulse. So that is called as a pulse modulation. So here we categorize again how we alter the carrier signal based on its amplitude or frequency or phase. So here again we classify the continuous wave system as amplitude modulation, frequency modulation, and phase modulation based on how we are going to alter the uh, alter the carrier signal based on these three parameters. Again here the pulse in pulse modulation, the carrier signal is a pulse, and the baseband signal is going to be a sine wave, and the carrier signal is going to be altered in terms of amplitude, width, and the position. So here we classify as pulse amplitude modulation, pulse width modulation, and pulse position modulation. So we'll study all these types of modulation in detail in the later chapters. Okay. And digital modulation, in digital communication systems we have again three different types of modulation. So one is the pulse code modulation, and delta modulation, and adaptive delta modulation. So here again, so all these concepts you will be studying in detail in digital communication. So again, there is one course which is going to deal in detail about all these types of modulation, which is digital communication systems. So in analog communication systems, we will study about all these modulations. So we will our syllabus is focusing only on these types of modulation, how it is modulated, and how we are going to detect it. Okay. Digital communication system, this is separate module. So this we will study in detail in the course digital communication systems. And as we see, analog signals are going to be a smoothly and continuously varying voltage or current. So examples, we have a sine wave. So it's a continuous waveform, and it's a voice signal. So this is a voice signal. So here again, it fluctuates with time. And video signal or a television signal. So it's something like this. Okay, so all these are examples of analog signals. And digital signals change in steps or in discrete increments. So most digital signals uses binary or two-state codes. So we have different examples here. One is the Morse code, continuous wave code, and serial binary code. So all these are used in computers. So this is the signals which are shown here. So first is the Morse code. We have the mark and the space. So high and low is expressed as mark and space, and this is dot and dash representation. And again, this is the serial binary code where we have the ones and zeros representation. Okay, so all these are digital signals representation. And next is classified based on the techniques of transmission. So one is the baseband transmission. So if we are going to simply transmit the signal without any modulation, so original or unmodulated information is transmitted directly, it is called as baseband transmission. But generally we don't prefer baseband transmission because the purpose behind modulation is we have to transmit the signal over a longer distance. The signal strength will get reduced, okay, and it is prone to noise and other factors. So that's why we have to modulate it. So this is the basic technique, which is the baseband transmission. And communication using modulation, so transmission of information signal with a carrier called as carrier wave transmission or passband transmission. So passband transmission, I'll tell you in detail what is passband. So since we are modulating it with a carrier, okay, so it is going to be shifted in terms of frequency. Okay, so that's why it's called as passband transmission. It is going to be in another frequency band. Once you are modulating with a high frequency carrier, it is going to get shifted in a other frequency band, so which is called the passband. So it's called as passband transmission. So it's also called as carrier wave transmission. And so types of communication, again here we have broadcasting and point-to-point communication. Broadcasting involves the use of single powerful transmitter and numerous receivers. And generally we know in radio and television we are using broadcasting. And point-to-point communication, in which communication process takes place over a link between a single transmitter and a single receiver. So that's point-to-point. So the radio broadcasting examples, AM and FM radios and television. And point-to-point example, satellite communication. So have you heard of satellite communication?
Yes, ma'am.
Satellite communication in detail. Okay, so we will have earth stations, one at the transmitting end and the receiving end. So we'll be using from the earth station, we will transmit to the satellite, that is point to point. And again, downlink. So we have the uplink and the downlink. Data is transmitted through uplink from the earth station to the satellite. From the satellite, again through downlink, we are going to receive the data. Okay, so that is point-to-point communication. So it's built around a satellite in geostationary orbit, relies on line of sight radio propagation, and for the operation of an uplink and a downlink. And this is the spectrum, electromagnetic spectrum. So here we have the various frequencies starting from extremely low frequency, that is from the hertz range, to extremely high frequency, which is 10 power 15 range, giga, and more than that, terahertz range. This is the frequency range. And we can see what are the different applications we are going to use in different frequency ranges. So let's say the power and the telephonic applications we will cover in the extremely low frequency to a very low frequency range, that is from 10 power 2 to 10 power 4. So this is again shown here. Okay, this is the table which shows you the exact frequency range based on the application. So typical application and the frequency and the corresponding wavelength. Okay, so as a EC student, one should know each frequency. Okay, so if you go to any interviews, this question will be definitely there. So what is the particular frequency range for this particular application? So you should this you have to buy heart. Okay, so you have to know the different frequency ranges for what applications. So just go through it. So we'll do some numericals based on this frequency ranges and all that. So if you want to work at a particular frequency range, so you have to use this. So if I say FM broadcasting means you have to use only this frequency range, 30 to 300 megahertz. So this is the frequency exactly we are going to use, that is very high frequency range. Okay, like this, just go through this table. Again, this is the picture showing you for a particular application what is the particular frequency. So still it is specific. So AM radio means it is 550 to 1700 kilohertz, and ultra high frequency televisions 460 to 600 megahertz. Remote controls operating from 100 gigahertz to 500 terahertz, like this. So we have different frequency ranges for different applications. And so okay, in this picture, it just show you here we have the frequency and the wavelength. So we know that frequency and wavelength are inversely proportional. Okay, and the size. So here it's mentioned about the size of the instrument that we are going to use. So here, if you see at high frequency, the size of the instrument used will be very less. If you see, as the frequency increases, the size is getting reduced. At low frequency, the instruments will be big. So if you see televisions or radio, so the instruments that are used will be big. Okay, and as the frequency increases, the instrument used will be gradually decreasing. So that is how this is relating. This picture is relating with the frequency and the size of the instrument, and also the wavelength. Wavelength is inversely proportional. The wavelength will decrease. And the concept of bandwidth and power in communications. Okay, so have you studied generally? You know about bandwidth, right? So we know what is bandwidth. It is expressed in megahertz and gigahertz, right? Or it is expressed in bits per second, right? So either we can use in hertz range or in bits per second. Generally, the different radio frequency communication offers different bandwidth. So you generally we use Wi-Fi. So the bandwidth is limited at 54 megabits per second. So generally the concept of bandwidth and the power, generally we know these are the two primary resources which are employed in the communication system: the transmitted power and the channel bandwidth. So these are the basic two requirements which are used in the communication. So either the bandwidth can reduce or the power can reduce. So some communications which it relies on the power, and some communication it relies on the transmitted that is channel bandwidth. So the transmitted power is the average power of the transmitted signal, and the channel bandwidth is defined as a band of frequencies allotted for the transmission of the message. So uh, therefore a general system objective is to use these resources efficiently as possible. So we can classify either as power limited or band limited. So if you take a telephone circuit, so this is typically band limited channel. So the telephone circuit, it is going to be dependent on the bandwidth. So if there are more users, so let's say for example, if a particular channel is being it is used by more number of users, the same bandwidth is going to be shared among multiple users. Okay, so the the telephone circuit is band limited. Okay, so there are some restrictions, right? Only these many users can use a particular band of frequencies. Okay, so that's the telephone circuit is a band limited channel, and whereas a space communication or a satellite channel is a power limited. So depending on the power that is used, okay, this kind of channels can be used, space communication link or a satellite channel. So these are the different examples for a power limited and band limited channels. So these are the primary resources basically in a communication system. So power can be expressed in dBW or dBm. So if it is the dBW is nothing but the power expressed in decibels relative to 1 watt, and dBm, it is the power expressed in decibels relative to 1 milliwatt. Okay, so there is a conversion basically from dBW to dBm. So you can check it. You can check the conversion. How do we convert? There are some calculators also, dBm to dBW to dBm conversion calculators available. You can use it. And these are the characteristics of the receiver. So what is called sensitivity? Then generally any receiver will have all these characteristics. So what's called sensitivity? So sensitivity is generally the ability of the receiver to reproduce a weak signal. So generally the we are, if we use a radio, if we use a radio, we are going to tune it. There is a tuner button, right? So we will tune it, and we will see which station can properly receive the signal. So receiver is part of the radio, right? Receiver antenna will be there, it is going to receive the signal. So the ability of the receiver to reproduce a weak signal. So even the signal received is very weak or feeble, it is the receiver should correctly receive it and able to amplify it. Okay, that's called any receiver should have good amount of sensitivity. Okay, and that is applied to the input terminals of the antenna or power at the loudspeaker or headphone terminals. It's also known as receiver threshold. So again, noise. So all receivers generate a certain amount of noise. It's the limiting factor of sensitivity. So generally, sensitivity should be high and noise should be less for any receiver. And selectivity. So selectivity means, so generally receiver you're tuning, receiver antenna of a radio will be tuning it. So it has to select that particular frequency. Okay, so if you're tuning for a AM radio means or a FM radio means it has to select a particular frequency. So that's called selectivity. So degree of selection of the desired signal or degree of rejection of unwanted signal. So it should not select all the signals. It should select only the wanted signal and it should reject the unwanted one. Selectivity is determined by the sharpness of the resonance produced by the tuning circuit. So generally, there will be a tuning circuit where it will tune that particular frequency. Then fidelity. So fidelity is again one of the characteristics. So it is the ability to reproduce the exact replica of the transmitted signal at the receiver output. So fidelity means, so how you send the signal, the same signal should be reproduced. So that's called fidelity. So any receiver should have good amount of fidelity. And double spotting, so it's one of the characteristics. So double spotting means we will receive two signals, similar signals. Okay, so you can't distinguish which is the original one, which is the unwanted one. So that's called double spotting. It's the condition where the same desired signal is detected at two nearby points on the receiver tuning dial. One point is the desired point while the other is a spurious or a image point. So we will study the techniques later, how we can remove this double spotting and all that. Okay, so these are the generally the receiver characteristics. And finally, what is called modulation. So here we have studied about baseband transmission and then transmission using modulation. So the purpose behind modulation, as I told you, here we will study why do we modulate the signal. There are different other purposes. Generally, the signal strength will be increased whenever we modulate it, and it has to travel a longer distance. So that's why we generally modulate it. So modulation is the process of translating a signal from one frequency range to the other without affecting the intelligence contained in the original signal. So we will not make any change in the original signal. Without affecting the original signal, it will be translated to another frequency range through a carrier signal. So that's called modulation. So the information in the original signal is contained in the modulated signal, either in the form of an amplitude variation, frequency variation or phase variation. So that's why it's called AM, FM, and PM respectively. So we have these three different types of modulation: amplitude, frequency, and phase modulation. So this is shown here in terms of spectrum. So here this is the baseband signal. So baseband means the message signal. So this is represented as plus FW and minus FW. So this is the spectrum. So this is spectrum means it is we are seeing the signal in the frequency domain. So all these days we are representing the signal in the time domain. Time domain representation means it's voltage versus time. So this is the frequency domain representation. So in x-axis we have the frequency, and in y-axis we can either represent in terms of voltage or power. Okay, and this x of t is the time domain. It is translated to the frequency domain, which is x of f. And so this is the pass band signal. So this is after modulation, this is getting converted into pass band. So here the frequency is getting shifted like this: fc plus fw and fc minus fw. So here we have two side bands, one upper and the one lower side band. So whoever have done the modulation, AM AM modulation, the modulated signal will contain three frequency components. One is the carrier, upper sideband, and the lower sideband. So this is how the spectrum will look like. The modulated signal spectrum, the AM modulated signal spectrum will look like this. Okay, and this is the again the frequency spectrum showing you the pass band. So this is how we calculate the bandwidth. So from the which is the difference of the two frequencies, upper and the lower side frequencies. Okay. So this is a general block diagram. How do we modulate the signal? So here we have the message signal. So which is generated from a sound signal, which is carried by a mic, and then we are amplifying it and sending it to a modulator. Again, this oscillator is producing a carrier signal, which is a high frequency signal. We are modulating it. So here any kind of modulation we can use, and then transmitting via an antenna, and then it is propagated through air as radio waves. Again, on the receiver side, we are using a receiving antenna, and then it is given to a radio receiver. So this is how we generally modulate and then transmit over air and receive it. So again, in the receiver section, we'll have several other components. It's not shown here. Radio receiver, simply here it's shown. So what is the need to modulate the signal? So the first factor is the reduction in the height of the antenna. So here, generally, if you do not modulate the signal, the antenna height will be very high, very high. So if you modulate the signal at high frequency, the antenna height can be reduced. So if a low frequency signal is directly transmitted to the free space, the size of the antenna required to receive the signal will be practically impossible to realize. So hence the signal must be modulated before they are transmitted. So you can see here, I'll just show you an example. Consider a signal transmitted having a low frequency, 4 kilohertz, let us take. Then size of the antenna would be, so now we are going to calculate the frequency, that is, sorry, the wavelength, lambda equal to C by F. Lambda is proportional to the height of the antenna. This wavelength is proportional to the height of the antenna, so which is around 75 kilometers. So it's practically not feasible. Okay, so now let us use the high frequency carrier around 40 megahertz. So after modulation, our frequency will be shifted to 40 megahertz. Okay, so it is coming in meters range, right? So this is the difference. The antenna height is reduced. So if you are going to modulate the signal, so this is one of the very first factor why we modulate the signal. And then the second one is multiplexing. So whenever we multiplexing, we have two different types: frequency division and time division. Multiplexing is a process in which two or more signals can be transmitted over the same communication channel simultaneously. So we can, in the same channel, we can transmit multiple signals. This can be done with modulation. So if you do not modulate, what will happen when you multiplex? All the signals will be in the similar range. So there will be more interference happening. So if you modulate, so they will occupy their own bands. Okay, so each signal will be modulated according to their own carrier frequency, and they will be in their respective bands, and there is the interference or the possibility of interference will be reduced. Okay, the multiplexing allows the same channel to be used by many signals. Hence many TV channels can use the same frequency range without getting mixed with each other, or different frequency signals can be transmitted at the same time. So this is how this is generally the multiplexing, how it is done. So we have different channels or n inputs. So this is a multiplexer. where they are multiplexed and then transmitted over a channel, and then on the receiver side we'll have a demultiplexer, and then they will be given to the corresponding end users. So again, this is just shown in terms of frequency users from the transmitter end and again on the receiver end. So this is what I said, avoid mixing of signals. So if the baseband sound signals are transmitted without using the modulation by more than one transmitter, then all the signals will be in the same frequency range, nearly 0 to 20 kilohertz. So therefore all signals get mixed and the receiver cannot separate them from each other. So if each baseband signal is used to modulate a different carrier, they will occupy different slots in the frequency domain. So we can avoid mixing of the signals, or interference can be reduced. So this is again the purpose why we modulate the signal, and improves the quality of reception. So without frequency modulation and the digital communication techniques such as PCM, effect of noise is reduced to a great extent. So right, so you can find the difference between the digital transmission and the analog transmission, right? So though in olden days when we are using analog transmission, you can see the noise or the signal quality is less, right? So if you use a digital version, digital communication, the signal quality is has been greatly increased. Noise effect of noise has been reduced. Okay, so all these are purpose behind why we modulate the signal, and these are the different types of modulation. So here we have continuous wave, and in continuous wave we have amplitude modulation and angular modulation. In angular we have frequency and phase, and in pulse digital modulation, we have digital modulation and analog modulation. So in analog modulation, we have pulse amplitude, pulse duration, and pulse position. So here we will use the carrier signal as a pulse. In continuous wave, we will use both carrier and the message both as a continuous wave.